Cool. Without further ado then, let's jump into things. Your first question might be, what's a breadboard? That's a kind of weird name. So, that's a breadboard. I also, if my camera is still showing, have one here in real life. If those are both on the screen, I'm not entirely sure. But if you cannot see my camera, it just looks like what it looks like here on the screen. And a breadboard is a way to build electrical circuits without needing to make permanent connections with, say, a soldering iron. So the way that you build circuits is you take a bunch of electrical components and you connect them together with wires. That's probably something you're quite familiar with. But what this does is, instead of requiring you to connect a whole bunch of wires by hand, and ways that you make permanent connections is with solder, so you like melt metal onto that connection, you can avoid all of that with something called a breadboard, which is what this is, because it has little bits inside of it that are connected. And then these little holes here, you can just kind of like press things in. It's a little bit like electronic Lego, sorta. So you can press things into the holes and then connect other components to them rather easily. So I'll demonstrate this in just a second. I would, of course, in an ideal world, show you a breadboard in real life and let you play with them. But since we're in the midst of a very busy apocalypse, I found a cool, I was told about and also found a cool resource online called Tinkercad, which is what we're going to be using to build these circuits and simulate them, but all digitally. So that should be something we can play with today. But before we jump into that, I'll explain what these yellow lines mean. So these breadboards have connections in a couple of different ways. You see that there are these rails here on the outside. And what these rails are the power rails for the breadboard. So usually you just have whatever your power source for your circuit is. You put your positive end of the connection here on the plus line, and then your negative connection in the minus line. And what happens is, if you plug in one power source thing down here or up here, they're connected all the way along this strip. So once you've connected one of these things to power, every single one of these holes is connected to that same power source. And that'll be a little bit more clear in just a moment. But the advantages of using a breadboard like this are that it's very easy to play with and experiment with. So actually, I have... I'll ask in the chat, can people see my webcam still? Or has that entirely disappeared now that I'm presenting? Because I can show you something in real life on my camera, but I need to know. We can see you. Excellent. Fantastic. In which case, I'll grab an example breadboard that I've had stashed behind my monitor for like 6 months. And it's much more advanced than anything we'll be doing, but it shows an example of what you can kind of like put together. So here, I'll press this down slightly. It's possible you can see breadboards on the screen or on my camera. Let me know. Maybe. Perhaps so. I wish I could double check. I can see. Fantastic. Okay, so yes. So these are just an example of a breadboard circuit that I built. It's actually got a couple of more complex components on it. Like this here is an ESP32, which is just like a little, what's called a microcontroller. And a microcontroller and Arduinos are just an example of a microcontroller. Those are things that we'll be going over next week and the week after. But you can see here, if I want to change around components, all I have to do is pull them out of this board and then stick them back in. So like this blue wire here is connecting, it looks like, power up here to this microcontroller. Over here I've got a bunch of different LEDs, which will shine up and show light signals. And then these little things, these tiny components on the side, are resistors. But we'll get to all of that today. But the idea of these breadboards is, if I want to, say, move something around, all I have to do is pull something out and then put something in a new hole. So it's all very temporary. So like this connection here or whatever, you can just take it out and then put it back in wherever. And in this case, I'm putting it back in a random place because I don't remember where that was connected, but that's fine. We'll figure that out some other point. Okay. So if you've seen electronic circuits before in, like, say, a laptop or some computer or some other electronic device, you've probably not seen a breadboard. And that's because these breadboard things are mostly just for testing, for prototyping, and then once you've finalized your design, you can create something more permanent called a PCB. So I think our next slide is a comparison of the two. Yes, so I also have examples of a PCB that I designed, which was pretty cool. But these things you design in a bit of software, and then you have to get manufactured elsewhere. So I'm not sure, can you see that? This little green circuit board here. Wonderful. Okay, yes, so this is an example of a PCB. So this is a quite complex circuit on here. It was originally made for driving a little tiny robot that would be underwater. So how it works is it doesn't have any of the components on it yet. So this is just like the breadboard. It doesn't actually have the electronic bits connected. So this is just all like the blueprint kind of for how everything gets connected. But what you do is you attach the actual components to all these little silver pads here. And these little tiny lines that you may or may not be able to see running through things, those are the wires. So in a breadboard, the wires just go for the mid-section horizontally, and then for the side sections vertically. But for a PCB, those can go in basically any direction you want them to. And you can build some pretty advanced things on this. These are probably the kind of things that you've seen before when you're opening up electronics, except probably with components actually stuck to them. But they can come in all sorts of shapes and sizes. So here's one that was supposed to hold a bunch of LEDs around the outside, and these were all an LED that had that particular square footprint is what it's called. So that's what it kind of connects onto. But PCBs are a more advanced topic. We might, if people are interested, second semester, talk about how you actually design those, because it's not too difficult. I mean, there's definitely a knack to it, but it's something that you can learn, and you don't have to be an electrical engineering major. Wonderful. So yes, just to compare and contrast the two. These PCBs, like I said, I was just showing you empty skeleton ones. For these to actually be functional, you need to do something called soldering all the components on. So you need to take all the tiny little components, melt some metal, and stick them to this board. With breadboards, you don't need to do that. Like I showed, you can just pull things out and put things back in. So yep, it's more temporary, whereas the PCBs are more permanent. And the PCBs, because they're very permanent, and usually because you need to ship them from like the other side of the world when you order them, you need to be pretty certain that they work, and they need to be thoroughly designed. Additionally, because even once you have the circuit, like the schematic setup, you need to position things correctly. So that's another thing to worry about. But breadboards, you don't have to worry about any of that. If you know the circuit, you can just go and put it together. So, to make that a bit more concrete, because that's been very abstract so far, I'm going to show you a cool website called Tinkercad. And there, we can start playing around with some of our circuits. So if you go to the website itself, you'll run into something like this, which isn't in itself terribly helpful, but what you can do is sign in or join if you haven't already. You can make an account for free. So I think, I don't remember how I signed in, but that's fine. We'll figure it out. I think I signed in with Google. Bum, 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 bum. Ah, but this is the wrong Google, isn't it? Sure is. Okay, let's try that again. Bum, 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 bum. Probably should have prepared this one, shouldn't I have? That's all right. Hey, there we are. Cool, we're logged in. Whoopsie. All right, so once you're logged into Tinkercad, you'll probably see something like this. So Tinkercad actually lets you do a whole bunch of different things. You can actually make 3D designs, like a normal CAD program. And CAD stands for Computer-Aided Design, if you haven't come across that before. So they're just like tools that help you design things, and the computer gives you lots of help along the way. So we'll be going over 3D CAD later in this course bootcamp thing. That'll be one of our last topics that we touch on, but we'll be using something called Fusion 360, which is a much more, I guess, professional environment than Tinkercad is. But it's good for playing around on. What we are interested in, however, is the circuits one. So here, you can build circuits, like whatever mess is going on there. So what we'll do is just create a new circuit, and you can do this on your own as well. You'll have time to play around a bit later, and I can help again there. So don't worry if you're slightly lost through like the button clicking here. And then you end up with this, a very empty screen. But you can see we have a breadboard over here in your little components tab. So what I can do is just go ahead and click on the breadboard and then click out here, and there we are. So here's our breadboard. Something helpful, when we roll over one of these connections, we can see that Tinkercad goes and lights up all the things that it's connected to, which is very helpful. So when we're rolling over this breadboard here, you can see those connections, I guess they're now vertical. And then the power line, that whole strip is connected there. So this whole thing is all connected. To make that a bit more concrete, what I can do is show off a, let's light up a light. How about that? So an LED, so I'll grab an LED from over there. I can put that down, I'll put it here, that has an anode and a cathode. And those LEDs are very particular, whereas like incandescent light bulbs, which used to be quite popular for late lighting rooms and things, where you could run power through those either way because you're just heating up a filament. LEDs are what are called diodes. So diodes, that's what the LED stands for. It's light emitting diode. The diode bit means that electricity can only flow one direction through it. So you need to be sure to connect these up the proper way if you want them to light up. But we can be sure to do that. So the first thing we'll do, let's say we'll grab this battery here. So batteries will just give us power of some sort. And then what we can do is connect the battery to our power lines. So in Tinkercad also you can rotate things with the R key. So I can spin it around that way or something. Then to draw wires, you just click on the place that you'd like to start the wire, you hover over it and it'll give you a little thing. You can click on it. Then I can do something like this, and then like that, and then go over and click on that. So then that wire is connected up to the positive line there. And I can do the same with the negative line. So we go over, and then go down, and over again, slightly at an angle this time. And can I grab that? Oh, sure can. How convenient. Wonderful. So then we have power running through there. Now, how do we know that we have power running through there? Well, we could try and connect our LED to it and see what happens. So the cathode is the positive end, I believe. We'll double check. And then the anode is the bit that needs to be connected to negative. So let's see. Actually, might not be happy about that. Let's give it a go. So we'll put it in that way. Will it connect? And simulation. Yes, fantastic. Cool. Okay. So, what I've done here is the anode, looks like, yeah, so I must have gotten that backwards. Sorry, that's my bad. So the anode is the positive end of things. On a real LED, this is a longer connection. So to demonstrate, I have a real LED somewhere here next to me. Wonderful. Right, so this one's going to be a bit small to see, but you'll have to let me know if you can see it. Can you at all see the ends of that LED? The little tiny bits sticking out of it? Or is that very, very difficult to see? Maybe if I put a background behind it, it'll be slightly easier to see. Is there any... Now I can't even see what you're seeing. Any luck there? Yes, exactly. So one leg is shorter, if you can see that. If you can't, you may have to take my word for it, and I'll be sure to get you a real LED to play with at some point. But the longer leg of the LED is the positive leg. So in this case, that means that the longer leg is the anode. So that's how you know which way to connect an LED in real life. And if it's one that doesn't have legs, if it's some weird LED maybe that goes on a PCB, there'll be other ways that that's labeled. But the cool thing about Tinkercad here is that we can do something called simulate all of our circuits. So we can press the Start Simulation button, and then we can see that our LED lights up because it's connected there. Now you also see that it's giving us a warning. That might be really small now that I think about it. So I'll read it off for you. But this warning here says the current through the LED is 61.9 milliamps, while the recommended maximum is 20. So it's saying that the lifetime of the LED may be reduced. So in real life, these circuits with LEDs often have things called resistors that will limit how much current goes through them. but we're getting slightly ahead of ourselves, so we'll get to that in just a moment, but we'll jump back to our PowerPoint. But what we can see here, though, is that these connections are working. We can also move it to the breadboard proper. So we'll move it down here, and I'll rotate it again. We'll bring it back to where it was in the beginning. Put it in there. So if I put it here, I'll now ask some questions of the audience. I'll put it here so you can give me nice numbers. So this anode here needs to be connected to the positive part of the battery. Does anyone want to tell me 2 places on this board that I could connect with a wire? So if I were to connect this to that, how would I do so? And on a real breadboard, these holes are usually too small, so you can't stick 2 wires in the exact same hole. So that's why you have these whole rows that are connected. So I can't click there directly or there directly, even though Tinkercad might let me. But I can click on any of these other open holes and connect things up. So where, if I wanted to connect this to positive, should I draw a wire? Between what things? And you can say in the chat or microphone if you're feeling brave. And I realize it may be difficult to like specify an exact location on this. So can you see these letters along the sign? Yes, so resistor from the positive rail to the positive terminal of the LED. Yes, so I think that is a good idea. So coming from the positive rail, which is what this thing here is, as was pointed out, I can start drawing a wire. But in real life, I probably couldn't go directly there, because this hole, this connection down here, is already occupied by the leg of the LED. And like I showed on my camera, they're pretty small holes, so usually the wires take up the whole thing. What other places could I connect to the end of this wire that would still connect that anode to the 5-volt rail? Any ideas? And you can give the coordinates or just a general idea of wherever. In the same row, yes, excellent, I would agree. So you take this wire and you just want to connect it in the same row, yes, which as Philip has pointed out is row 20. So you could connect it here, or here, or here, or all the way down there, doesn't really matter. In real life, it's often nice and neat to keep wires short, because it means you have to cut fewer wires, or there's less hanging around. So I would do that and connect it to the close one, and that's connected it up in the same way. All right, and then similarly, I won't quiz people on this one because I think you've got it figured out. To connect this rail here, which is the cathode, to negative, we do the exact same process, except now we connect it to the negative rail instead of the positive one. And now if we simulate this, we see our light turns on, same as before, even though it's obviously still giving us the same warning, and we'll fix that in a little bit. So that is the basics of how breadboards are interconnected, where these rows here, as you can see, are highlighted, are all considered the same wire, and then these big power columns are the same as well. So I'll do a quick poll asking how people are feeling about breadboards. Bum, bum, bum. Breadboards. And I'm hungry is an entirely reasonable answer. Me too. I wish I could eat breadboards. Maybe not. Might not taste excellent. But you never know until you try, I guess. Are there any questions about breadboards before I move on? And there's never no such thing as a silly question. So if you're curious, just let me know. And I can hopefully help clear things up for you. But if not,
I was wondering whether, like, so as you said, on the sides, the wires are only like straight,
mm-hmm.
and in the middle is like horizontal. So can you make only those sort of circuits with breadboards?
Yeah. So that's a good question. Very good question. That's not where I want to be. There we are. So you can still make most all circuits in this way. This might look initially a bit limiting here, but say if you wanted to connect well, okay, so something we'll be doing later is connecting up a resistor to this. And a resistor limits the amount of current that's flowing through here, so that gets rid of that warning message. So a way to build that sort of circuit would be to put things, oops, resistors can go either way, and I've messed it up twice. There we are. These can go either way, so you could do something like this. Now what we've done is we've connected, the powers remain connected the same way. That's just a straight line, like you see. This here is, again, just a straight line. But now this whole line is also connected to this LED. So now both this row and this row are connected, just this row has to pass through this resistor first. So we could do something like, if I were to move that down one, then we could do that. And then that will still power the LED because the power runs now through the power line down into this row. It'll power everything in this row, which includes this resistor. It'll go through the resistor, then everything in this row, which includes the LED, so it'll go through the LED and then back. So yes, you can only make things that fit into these rows and columns, but because you can also connect different rows in this way, where you can put components across them horizontally, you can build just about any circuit, at least basic circuits. If you need some special orientation of the actual wires and you're doing things with like electromagnetics, then you're probably not going to want to be using a breadboard. But these, yeah, so you can build complex circuits out of them, but yes, you are correct. Just these rows are connected across, and then just these columns are. So that's a very good question. Does that answer your question?
Yeah, thank you.
Excellent. Okay, cool. Happy to help. Wonderful. All right. Yes, that was a brief look at Tinkercad. It can do a whole bunch more. We'll be using it a bunch over these next couple of weeks because it also lets you program Arduinos in it virtually, which is helpful, seeing as, unfortunately, I cannot give you real Arduinos. But that is all right. Yes, so a helpful thing to know how to do with circuits is measuring voltage and current. So I wanted to put like a nice picture here, but I didn't get the chance to. So you can measure voltage and current with tools called multimeters, usually. And those look a little bit like this. So I have one on my webcam here. This is what a multimeter looks like. It has these connections down here. And in there you put these little probes. I could get an example of one of those. Sure, one moment. So I'll grab both of these. It's a good thing I have a massive collection of electronics garbage right next to my computer, isn't it? Wonderful. Cool. So these are what the little probes look like. You get bits with some spiky metal on both sides, so you can use this to poke your actual circuit. And then you also have these ends, and these are the ends that connect into the multimeter. So if I go here, and you connect the things to these, or to different ports on here, depending on what you're measuring. So normally you'd have them connected like this way, and it tells you that because the middle one is COM, which stands for the common ground, which is what black is. So black is usually ground. And then over here is for if you want to measure voltage, or the little omega sign is resistance. And then it also has milliamps, which is current. So you'd plug them in like that. Then what you do is turn your dial to whatever you want to measure. So if I want to measure voltages, I turn it over to this voltage section of the dial, pick how big, and then you can see it gives a readout. And that changes depending on where I put these little prongs. So that's how they work in real life. And that'll make a lot more sense once, hopefully, you get the chance to use one hands-on if you've not already. But some very important things to know when you're measuring with them is that voltage you need to measure in parallel with a component, and current must be measured in series with a component, which means they come one after another. And I'll show you what that means in Tinkercad. So if we jump over here and we want to measure, say, how much voltage is coming out of our battery, which is sane to do. We know it's probably 3 volts, seeing as that's what this battery says on it. But we can double check. You can use this to, in real life, check if a battery is charged or something. So very down at the bottom of these components, you see there's a multimeter. So we can grab that, put this out here. You see we can choose between amperage, voltage, and resistance. This has fewer options than that real life one because this virtual one can do whatever scale it needs. It doesn't need the different machinery in that one for different sizes of voltages or whatever. So say we want to measure voltage. To do that, we need to measure in parallel. So to demonstrate what parallel and series mean, I'll show an example with, say, some resistors. So here is a resistor. Here is another resistor. And if I do that, and it's kind of not terribly easy to, oh, aha, there we are. There we are. Oops, can I just have it a board there? Maybe not quite. So maybe I need to actually connect it to something, which makes sense. Sure, so we'll connect it out just to the breadboard randomly. So these two resistors here are in parallel. And the reason that is because the power can come up here, up this wire, and it runs through both of these at the same time, and then out the other side. So that's what a parallel configuration looks like. A series configuration means they come one after another. So you'd have something like, there's a resistor, and you connect them like that, and then the ends of that are connected to whatever. So in this case, I'll just do those. So these resistors are in series, these are in parallel, and that'll be important in a little bit later. You can see those on a circuit diagram a bit nicer in a bit. But for our voltage measurement, we need to remember to connect our voltmeter in parallel to the component. So if I wanted to measure the voltage across this resistor here, I would do something like put a wire, and I'll do this, I think, on, no, it's fine. One wire there, or sorry, there. So that's one side of it. And then the other side is over here. And that would be in parallel. And I'll actually move this down so it looks a bit cleaner. Oops, that's not what I wanted to do. There we are. So that is in parallel because the electricity can run through this resistor, and it also gets encountered at the same time by this voltmeter because they're both connected in the same kind of side there. So if we were to simulate this circuit, we can go ahead and simulate it, and we see that what that resistor doing, or that resistor across it, has 1.16 volts. So we'll see more, again, the significance of that in a minute, and how that's related to current. But if we want to measure, say, a different thing, so if we wanted to measure our battery, like we initially wanted to do, then you can just come over here, we'll connect the red to the positive, and then the black to the negative. So that's measuring the battery. Again, we're in parallel with the battery. We can start that. And here we get nearly 3, so we're slightly short of 3. But 2.99, that's pretty darn close to the rated 3 volts of the battery. I'll move that just back up. But if we wanted to measure the current running through something, so you remember earlier our LED complained about current. Current you measure in series. So to do that, what we could do is break the circuit here so that the circuit is no longer connected. And then you connect it through the multimeter that you want to measure with. So you could say, well, yeah, sure. So there's your negative. And then on this side is the bit that connects to the LED. So now the electricity cannot just go back to this negative line directly. It needs to go first through the multimeter. So that's the difference, I guess, or that's it in series. So we also need to change this to measuring amperage, which is the measurement, or the unit of measurement of current. And then we can start that. And you can see that it's got negative 1.6 milliamps. Now, in this case, the reason that that's negative is just because of the way that these probes are connected. So if I connected the positive one down here and the negative one up here, then it would be positive 1.6 or positive 1.16. But that is how you can measure current with something, by putting it in series. And you can see that we definitely know it's in series because if I take out the wire connecting the multimeter, then the circuit does nothing. The LED no longer turns on because there's no connection there. Okay. That is, that may have introduced some additional questions, but we'll get to those in just a minute. Do people have any questions about how you measure voltage or current with a multimeter? How are people feeling about that? We'll create a poll. and feel free to ask any questions that you have about that using multimeters. In real life, it'll be one of your best friends when you're debugging circuits, because unlike in Tinkercad, where you can often like hover over things and get information about them, you cannot do that in the real world, as convenient as that would be. So your multimeter is often your only way to see what's going on when your circuit isn't working the way you expect it to. Okay. Cool. There are fewer positive feelings than before, but that is all right. Maybe people are still just rolling in. If there are no direct questions about them, I could move on, and then we'll probably be revisiting multimeter use, I think, throughout. Any last questions before we go? Cool. All right. In that case, we'll hop on to our next thing here, which is some common formulas. Now, this is phrased here as a reminder of common formulas, although it also occurs to me that you may not have seen all of these before, so perhaps it's the first look at some of them. In which case, I'll try my best to properly explain them. So the first one is perhaps the most important that you'll come across, and that is Ohm's law. So what this says is that the voltage across some component is equal to the current going through it multiplied by its resistance. So that allows you, so say our resistor earlier in Tinkercad, oops, gone backwards there. Our resistor earlier here in Tinkercad, when we measure the voltage across it, we can use that to calculate the current across it. Of course, you could also measure that directly in this case, but we'll do this for an example. So there we are. We'll measure the voltage again. So if we go ahead and run this, then we see that we have 1.16 volts. So that would be whatever is on the left side of our equation here. So we'll have, oops, I got stuck in there. We'll have 1.16 volts. So here I can actually pull up a calculator even. So we can calculate it. Oops, nearly. So we have on one side our 1.16 volts, and we want to calculate current, say. So if we want to calculate current, you'd rearrange this equation here. So you'd have I equals, and then you'd move the R over to underneath the V. So it'd be voltage divided by resistance equals current, and that's just by dividing R from both sides. So in that case, we have our voltage already. Now we just need to figure out our resistance. So our resistance, we can figure out, whoops, that's not entirely what I intended to do there. Whoops, we jumped forward and managed to unfull screen it. That's impressive. Okay, there we are. We'll bounce back a couple. And yes, you did see a sneak peek. There will be a Kahoot quiz. How fun. Right, so yes, we know our voltage. Now we just need to know our resistance. In the real world, you need to read that from the color bands on this resistor. I won't force you to learn that because it's something that you can usually find guides for. But these color bands do indicate the size of a resistor. In Tinkercad, you can just click on it and you can see up here what the resistance is. So it's currently 1 kilo ohm, so that is 1,000 ohms. And we can change that to be different values. So actually, if I'm allowed to change that while the simulation is running, you'll be able to see that the LED will get brighter. So I'll change it to, say, 330 regular ohms instead of kilo ohms. And now you see our LED is brighter than it was before. And the reason for that is there's some more current. Oh, we've also changed the voltage. So if we take our new voltage, which is 1.08, divided by 330, we'll be able to get the current. So we'll take 1.08 divided by our 330, and we get back out of that a really, really gross number. And that gross number is gross because amps are really large units, and that's what it gives us this in, is amps. What you usually measure things in tiny breadboard circuits like this, is milliamps, which is 1/1000th of an amp. So to convert that, you can just multiply by 1,000, and then we get something like 3.27 repeating, it looks like. So let's see if that's true. We'll try and make a measurement of the current running through this resistor by putting this thing in series, and we'll see if it works out to be 3.27 milliamps, or something around there, in that ballpark. So I'll stop the simulation really briefly. We'll cut those wires, move that down. We'll get rid of that, because we want to replace that connection with the multimeter. And now, if we simulate that, oops, that's not right. I need to change that to measuring amperage. Current, wonderful. Hey, look at that. We have 3.26. It looks like it's actually rounding that, which is convenient because, oh, no, never mind. It should be 3.27 either way. That's fine. But here, yeah, you see 3.26. So that's only off by 100th, so that is perfectly reasonable. This simulation actually might be keeping or taking into account the very, very, very tiny resistances of regular wires and things. But you can see that our calculation there, our Ohm's law, worked out. We'll be doing plenty of practice with that as we go along, but are there any questions about Ohm's law before we get any further? For the most part, it's just rearranging some variables and then plugging in some numbers and remembering that it's in amps, not milliamps. Any questions? Cool. All right. If you do have any that come up, just feel free to drop them in either of the chats. I'm watching both. So, lovely. The next equation that we have here is power. So sometimes you might want to know how much power something is using or is dissipating into the environment for a variety of reasons. Oftentimes, if you have power supplies, which provide electricity, so these are things that are bigger than just, a battery, those will have limits on how much power they can safely provide before they get it, well, a little burst into flamesy. So it's sometimes it's very important to know how much power your circuit is going to take, because if your power supply can't handle supplying that much power, then your circuit won't work. So power is measured in watts. So that's the unit there. So power is in watts, and then the equation for it is quite simple. It's just the current multiplied by the voltage. So if we were to look at our example, hey, we get to bully some people into thinking on their feet. Wonderful. So if we look back at our example here, and I'm not sure how tiny this calculator is. Hopefully the numbers are somewhat visible, but if not, I'll read them off. Our voltage was 1.08, so that was our voltage across our resistor. And then the current going through our resistor was this big long number here. You can think of it as 3.27 milliamps. How much power would be going through this resistor? And in real life, this power is in the form of heat, so it's given off as heating. So if you ever looked at a heater and it says it's a blah-blah-blah watt heater, that's where this calculation comes from. So the higher the wattage of the heater, the more heat it actually gives off. Power is directly related to energy. So what do people think our power dissipated by this resistor would be if the current across it is 3.26 milliamps and the voltage across it is 1.08? Anyone want to get brave and calculate that? I don't know if anyone's got a calculator nearby. Or you could even just give a ballpark, because one of the numbers is very close to 1. Any ideas from the audience? I'll give it a second for people to scramble and find calculators if they'd like. Okay. So, in the absence of an answer, I guess I'll show you all what I mean. It's just a very basic calculation. And I guess it probably, to be fair, would have been nice to keep this on screen for you, wouldn't it have been? So power is, again, current multiplied by the voltage. We now know both of those values for our resistor. So we can go over to our calculator even. And from here, our current, we can take this number here. This is in milliamps, so we need to keep that in mind. The equation or the calculation will still work, but our result will be in milliwatts, not actual watts. That will be the only difference. So if we do this, take our current, multiply it by our voltage, which was 1.08. Then, very, very similar number. This resistor is dissipating 3.5 milliwatts of power. And resistors in the real world, you need to be careful not to dissipate too much power with them, because just like power supplies, they tend to get a little explodey when you put too much power through them. So resistor power ratings. So resistors also have power ratings on them. So, well, this looks like a really nice example. Dun, 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 dun. Oh boy, it's bringing me to a random website. That is far more excitement than I'm in the mood for at the moment. All right, so here is the same picture. So you can see that some of these things are only rated for 1/8 of a watt, which would be, so if we take 1/8 of a watt, remember that number we just calculated was in milliwatts. So if we take 1/8 and then multiply that by our 1000, try 10 more there, Brooks. So these resistors, these really tiny ones, those would be able to handle at most 125 milliwatts. So we know that the power we're running through this thing, which is only 3.2, that's more than enough capacity for them to handle. And you can see, as you need to dissipate more and more power, the resistors get physically chunkier so that they don't melt or burst into flames. So all the way up to this massive 5-watt resistor here. So fun fact, I guess, maybe fun, electrical heaters, or like your toaster even. Toaster is probably a good example. All those little wires that get really hot are basically just resistors, and you're pumping a whole bunch of energy through them, and then they're dissipating this power, and that's what we're measuring here in watts or milliwatts. So, does that make sense to people? Are there any questions about that? We'll have a poll about Ohm's law and power. Oops, that was a lot of typos. There we are. So those are the two of the basic equations there. And those ones are quite helpful so that you don't blow things up, or, well, actually, yeah, primarily those two are good for not blowing things up. Because if you put too much current through an LED, you'll break the LED, and if you put too much power through a resistor, it'll go up in smoke. Wires as well. I'm not sure where it is. One of my breadboards over the summer, I did not follow my own recommendations and ended up putting too much power through something and melted part of the breadboard. So breadboards melt. That's good to know. Try not to do that, though. Excellent. Okay, so 4 people have responded yes, that they're doing all right about that. The rest, the jury is out, but that is all right. We'll proceed tentatively, and if you have any questions, then let me know. Are there any questions before we move on about power or Ohm's law? All right, nothing off the top of people's heads. And if I interrupt you by saying nothing off the top of people's heads, but you're actually typing something, please do continue to type it. It's just I can only see if people are typing on the Discord, and I can't actually tell if people are writing in the Google chat. But I'm watching both. Okay, so that's what power is all about. If you have several resistors, like here, these are in series, so the total resistance of a circuit is equal to just those resistances added together. So that one's pretty basic. I can demonstrate that in Tinkercad, I think. So if we go to Tinkercad, here we are, shop. Those are in series. Right, okay, so this one here, this resistor we've got, I should stop the simulation first. So this resistor here, hello? Am I allowed to look at that? There we are. Is 330 ohms, but you can also create an equivalent circuit or amount of resistance with 2 resistors that add up to that. So say we had one resistor here. Hello, can I edit that, please? There we are. That is, and we'll go into ohms. One that is 30 ohms, And then we'll have a second resistor. Can I copy paste? Sure can. And a second resistor that is 300 ohms. So actually, another thing our multimeter can do is measure resistance directly. So if I take that resistor there, and then also build a little circuit like that, we can measure the resistance of both of them. So, you were fine up there. We want to change the mode to resistance mode. Then you just directly connect whatever circuit you'd like to find the resistance of to. So that would be this one here. And if we run this, we see very much as we expect are 330 ohms. And that is because it's just a 330 ohm resistor. In the real world, things aren't perfect, so you might get some slightly different numbers. Not quite as ideal as this is, but that is the idea. And if we took, or actually we can do 2 multimeters simultaneously. If we have a second multimeter, this one also measuring resistance, but this time here and here. So if you think about this is 2 resistors in series, right? Because power can come out of this line, it goes up here, and it gets to this column where it disperses, and then it can go through this resistor, down through this one, and then back out into the measurement tool. So if we go out and run that, we see both of those are 330 ohms, and that's because they add when they're in series like that. So that's a good one to know. That one's quite helpful and decently straightforward. If one thing resists a bit and you add a bit more resistance, the combined resistance is just them added together. That's pretty basic. One that's a bit more peculiar, perhaps, is resistors in parallel. It looks quite intimidating, but what it really is it's the exact same equation as resistors in a series, except everything is flipped over. So you have things in inverse. So it's 1 over the total resistance is equal to R1 and to R2, or both underneath 1. So to show an example of that, we'll put some resistors in parallel in Tinkercad. So here we have 2 setups, 2 circuits here, and we know that both of them are 330 ohms individually. So I'll move this down, and I'll move this one here. Excellent. Right. So these are still separate, by the way, because these resistors only connect here at the very end terminals where you see those metal bits. These middle 3 holes are still totally unoccupied, so this one is still a free row that only has this upper one in it, and this one down here is a free row that only has this upper resistor in it. But if we were to put those in parallel, so if I connected this to the end of that one, and this to the end of that one, now essentially what we have is 2 330 ohm resistors in parallel. Because this one, remember, we've already determined to be 330 combined. So let's try and predict what our parallel resistance of these 2 will be. So to do that, we'll hop to our calculator. And we will take 1 over 330, because that's what one of the resistors is. So that's one of those things. Then we add the other one, which is actually the exact same. So we'll do plus. And then again, 1 over 330. And this gives us a number. But that doesn't look like a resistance. That looks pretty unhelpful. That would be very curious if it were that small, like much less than a singular ohm. And that's because what this equation actually gives us when we add the reciprocals is the inverse of the total resistance. So the last thing we need to do is take 1 and divide it by that number that we just calculated. And that will flip this thing upside down so we can get our total resistance. So if we do this number we just calculated, and we do 1 divided by that, then we get a value of, and that looks like just rounding error there, so it looks like 165 ohms. So if we go and measure that and test to see if our prediction comes true, oh, whoops, managed to mess that up again. So if we measure across this entire thing, which we can do by drawing, I'll do it from down here, doop, and doop, doop, try and make it look somewhat nice, doop, and there. So that's connecting, oh, just kidding, it is not connecting to that. There it is, now it's connecting to that. So this end is connecting to both resistors, both this one up here and this one down here. And this one here connects out, so, whoops, I drew that the wrong way. Sure, we'll have some wild shapes there. As long as they're connected, it should work. and then we can start our simulation. And bum-ba-da-ba-ba-da-ba. Hey, look at that. We get back 165 ohms, which is exactly what we predicted here, which is with our 164.9999999. Lovely. So that's how resistors combine in parallel, and that's helpful to know sometimes because these resistors in the real world come in finite values. Like you just get a pack of a bunch of 330 ohm resistors or something. But sometimes you calculate, like for one of your circuits, you'd like a resistance that you don't actually have a resistor for. So you could go out and buy a resistor that fits your exact value, but that might be really hard to do depending on what that value is. So this is a way that you can take resistors you already have and combine them to get the resistance value that you want. So you wouldn't even need to own a 165 ohm resistor to get a circuit that is equivalent. Does that make sense, the motivation for that and also the calculations? Are there any questions about that? Because that's a bit wacky and a bit hard to do without, or hard to grasp without practice directly. There'll be a bit of practice here in a moment. But how are people feeling about that? We'll create another poll. And are there any questions about like what resistors are for or anything? Because to explain that, they're mostly just for limiting current, because sometimes you don't want to let a bunch of current flow through something because it can damage it. So that's the main idea of a resistor. Any questions from anyone? Any things that are confusing? The number of I'm feeling good about these things has decreased steadily over time. Okay. So if I were to, let's do an example together real quick. Okay, we're up to 4, we're up to 5. Hey, look at that. Okay, people go seem to be doing all right. Okay, there will be an example again in a minute on a Kahoot quiz actually. So you'll be able to try this out for yourself, and we'll go through the problems, and hopefully I'll be able to explain them. Cool. Alrighty. So, whoops, that's again the wrong place. The last thing we see here is something called a voltage divider. So this can be kind of helpful if you want to get a voltage output that is different from your input. And the way this works is that you can calculate how much voltage each of these resistors drops, and then you can take the voltage from the middle, so after you've dropped some certain amount, and then the rest is dropped all the way later. Those are slightly more advanced. I actually reckon we'll come back to this once we've done one of our later slides, and I'll explain how this works. This equation here, though, you can derive it entirely from these existing equations, so you don't need to memorize that if you don't want to. Those will cover that. They encompass the whole thing. So moving past that. Okay, yes, so parallel connections versus series connections. So we've seen kind of the differences between those a little bit. So we'll get to the Kirchhoff laws in just a moment. But it's worth saying, or worth pointing out, that when I have voltage across, say, two things in parallel here, so if we were to put a voltage across this circuit, so there's power running here, going through both those resistors and coming out the other side, whatever voltage I put across here is identical to the voltage that both of these see. So if I put our 3-volt battery, which is certainly somewhere, if I take our 3-volt battery, connect, oops, that's, right, so I didn't even build this circuit properly. So we'll just get rid of those wires for the time being. And there. And if I move that, that'll look a bit nicer. Okay, so this 3 volts voltage, it's going to be the identical voltage across both of these components. So this resistor has 3 volts across it, and this one also has 3 volts across it. It doesn't change for the two of them, so I can show that off. We can do delete, and measure with this voltage, and then go here, measure this first one, I guess. Oh, will it even let me? It might not. There. Oh, it's a bit angry about that. Click. And then here, same one. If we go ahead and measure that, start the simulation, you see. So we actually get slightly less. The reason for that's a bit complex, but this battery itself, all power sources actually have a little tiny resistance of their own. So as current starts flowing, as Ohm's law says, so the voltage that's lost is equal to the current that's flowing multiplied by the resistance. So if this has a tiny resistance and electricity is flowing through it, it loses some voltage. So here's maybe an example of it losing some voltage. But you can see it's pretty close to the 3 that it starts at. And if we move these probes to be on the second resistor, on the outside, you'll see exactly the same thing, which is probably or potentially obvious from just the way that this circuit looks. But it's sometimes a little bit less obvious when things are spread around. But as long as they're conceptually in parallel, the voltage across both of them is the same. So you see our same number a second time here. Now in series, the voltages change, so they add together. So the voltage across this resistor plus the voltage across this resistor is the voltage across the whole thing. But current is constant through something like this. Because if you think about it, current is the flow of electrons in a wire. So those will flow in a direction, but if it's flowing down this wire and it gets to the end of this resistor, it has nowhere to go except to into the next resistor. So it's not like the current can just escape, at least not in an ideal world. There are weird effects that make that possible, but generally speaking, the amount of current going into this bottom resistor would be the same as the amount of current coming out of the top. So it's a closed loop, and no current is like lost, I guess. So that's just explaining this slide here, but I think what we went, we'll jump into the rest of it soon. Okay, it's time for a Kahoot quiz, if people are feeling enthusiastic about that. I would recommend, some of the questions are easy, just like you can look at them and see. A couple of the other questions that have a longer amount of time, they'll give you a whole minute for them, involve some basic calculations with what we've just seen. So actually, when I do this Kahoot quiz, I will be sure to keep the equations on the screen at the same time as I have the quiz up, so that way you don't need to have those like written down or whatever. Well done, Brooks. That's not what you want to do. Okay, lovely. And whop. And we'll squish that over a little bit. Lovely. And I don't know if I can get that to go away. So this here is an equation. Oops. Can you see these equations here decently, by the way? Can you paste the link somewhere so we don't have to type it out? Yes. Don't worry. The way the Kahoots work is that once I actually start the thing, there'll be a little easy code that you can put in, and yes, I will give you a link to that. So this link is just if you want to run the quiz. So yeah. Can you see these equations here decently, or should I enlarge that slightly? That makes no difference, surprisingly. Okay, actually, it's bigger the smaller I make the interface. Sure, let's do something monstrous like that. Okay, can everyone see those all right enough, those equations there? Okay, cool. Excellent. Lovely. In that case, I will... Yes, and by the way, all of this session, I can't take credit for it, for all of it. I've been working with Bhumika, who's another member of the committee who you may have met before. Lovely person. She's currently helping out with a load of different things and helped me with this session. So she created the Kahoot for us. So we can go ahead and... I'll just play as a guest. That's fine. Whatever. Okay, and we'll do nice and classic. And now, what we do from here is it'll give us a game pen in just a minute. And there we are. We have one. So, with that game pen, what you want to do is go to www. I mean, it gives you the link there. But yes, so somebody's already figured it out. If you haven't yet, you can go to that link there. And then from there, you can type in that code that you see. And that will take you to the Kahoot. And you can put in a name, and we can answer some fun questions, hopefully. Wonderful. Let's see. We have... one. Of course it doesn't count myself. So we have 7 people in the call. Not everyone has to join, but the more people who join, the more fun it is. And for this, it's just good to have, I guess, a little bit of scratch paper and a calculator, but nothing is going to take a bunch of time. It's nothing too terribly hard. We'll just be playing with these equations mostly. Cool. Is anybody struggling to get into the Kahoot, and would they like any help? Excellent, we have 4 people. And additionally, is there anyone who doesn't want to participate in the Kahoot? Because if so, that's fine, but it would just be good to know prior to waiting for everyone. Okay, excellent. So we've had one person head off. Okay, we have 5 people here, 6 people in the call. So let's see who's not joining. I'm not entirely sure who has yet to join, but that's all right. We'll start in a second. Fantastic. Hey, there we are. Excellent. We've got everyone. Wonderful. Cool. Okay, so we'll start off then. The first one you won't need a calculator for. You will for the second one, probably. Or you could do it in your head, maybe. But we'll give it a go. All right. So the first question is, and you should see on your device, it should pop up with your answers that you can answer on. Which of these LEDs is connected correctly? And neither of them have power to them just yet, but the correctly here means that you could connect power to them and it would be functional. So you don't want the 2 terminals of the LED to be connected together. All right, we've got nearly everyone answered. All right, there we are. So there's also, yeah, a 30-second timer on that one. But hey, look at that. Everyone got it correct. The correct LED was blue, or everyone who answered anyways. And blue was correct, of course, because it on the breadboard... Whoop, 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 whoop. Oh, interesting. I can scroll on that one. On the breadboard, the anode and the cathode are in different column or different rows, so they're actually separately electrically connected. If you moved it here... hello, that was not the moving that I would like to have. Maybe it won't let me move it. That's fine. New LED. If you connected them both like this, you can see both of those are connected to the same wire, so you couldn't possibly get a negative voltage on one and a positive on the other. So that's why blue is correct. So well done, everyone there. So we'll jump back to give you some equations, and then our next question. This next one's a bit longer and is one that's a bit more mathsy. Hey, look at that, Maria, really fast there. Excellent, we got a whole scoreboard. Everyone who answers on it. Wonderful. All right, next one. What is the total current I if the voltage supply is 5, and then R1 and R2 are 5 and 10 ohms? And then here's your picture. So this voltage supply here is 5 volts, and then this resistor is 5 ohms, and this resistor is 10 ohms. So what is the current running through the whole thing? And we've got plenty of time for this one. All right, 15 seconds left. And no worries if it's a bit fast. Kahoots are always a bit hectic. Wonderful, we got 5 answers. All right. Hey, look at that. There we are. Everyone's gone ahead and gotten the correct answer again. Yes, so the calculation for that one, of course, is just you take your Ohm's law and, well, okay, so we know from series that these resistors add together. So the total resistance is 15, because 5 plus 10 is 15. Then all you need to do is take your voltage divided by your resistance, and that'll give you current. So 5 divided by 15 is the same as 1/3, which is the same as 0.33 amps. So that's how we get to that. So excellently done, everyone. Fantastic. Move on to our next one. Hey, look at that, some shifts. Phil's moved up the leaderboard. Maria's still holding strong in first. Ange is up on the board. Fantastic. All right, we have another one that's a bit mathsy. So this is a very similar looking question here, but the circuit is a bit different. So this time you have your voltage of 5 still here, but now your resistors 5 and 10 are in parallel. So your total resistance is going to look a little bit different. And as a general sanity check when you're doing these sorts of things, when you put two resistors in parallel, the resistances are smaller than either of them individually. So with a smaller resistance, you should expect a bigger current than you got last time around. But to be fair, all of these are bigger, so maybe that doesn't help too much. Okay, so a bit split there. So here is the correct answer of 1.5 amps running through the total circuit, and somebody's also answered 3.3, which is, I'm not entirely sure what the confusion there is, but we'll work through it and we'll see if we can find it. Because sometimes you just forget a little tiny thing, like maybe forgetting the 1 divided by something to like flip the total resistance at the end. But we'll walk through it real quick. So if I go ahead and grab my calculator, which hopefully people can still see, and we'll clear that. First thing we want to do is calculate the total resistance. So for that, we're going to need our parallel resistor mode. Let's put that in, that doesn't need to be fancy mode. There we are. So our resistors in parallel, we need to take 1 divided by each of our resistances and add those together. So one of our resistances is 5, and the other one is 10. So you can do 5 and then plus 1 over 10. Gotta get my brackets in there correctly. So that will give us 1 over our total. But when you have that, you need to remember that the actual resistance is 1 divided by that. And so the total resistance of our circuit is 3.3 repeating. So maybe that's where you got that answer from. That's the total resistance. But to find the current, which is what we're after, we need to take our voltage and divide by that. So our voltage, which was 5 divided by that total resistance, gets us to 1.5 amps, which is the current, and that's coming from the Ohm's law side of things. Does that make sense? Is that clear? Did that clear up any confusion there? Potentially. I won't make you say so if so, but yes, wonderful. Yes, and if we're more confused about that in the future, we can always go over it. But majority of you seem to have got it, and you just probably forgot the step at the end there, but you got most of the way there, which is wonderful. All right, so scoreboard. Ooh, and just moves from way up. A little bit of movement there. Maria and Phil still holding strong up in the top positions. Look at that, very fast answers. All right, wonderful. This one I think is another maths one. Okay, so what is the total power if the voltage supply is now 12 volts? So these are all different numbers. So 12 volts here, and this is 3 and 7 ohms. So what's the total power? And remember, power is voltage multiplied by the current. So first you need the total current and the total resistance, or total voltage, which you know. Wonderful. 5 answers in. Near time. Wonderful. Hey, look at that. Again, most everyone has gotten it right. We have one answer there that was not quite right, but that's all right. We'll work through it and we'll figure it out. Yeah, so it looks like... yeah. So the 120 watts, that's an easy confusion to come across, I think. Because I assume what you've done there is taken the total resistance, which is 10 ohms, because you're adding 7 to 3, and multiplied that by the voltage. But multiplying the voltage by the resistance doesn't actually give you power or necessarily current there. The correct way to go about it would be to take your total resistance, which is 10, as you correctly figured out, I believe, and then the 12 volts. So here you have your voltage, you have your resistance. Now you can find the current, because you need the current for the power equation. There are versions of the power equation that don't have current or don't have voltage, and that's just because you can always get it from Ohm's law. But in our case, we're just using the regular power equation. So here we would have our 12 volts divided by 10 ohms. So I'll do that in the calculator, even though that's just 1.2. We'll have it there in the calculator. So 12 divided by 10. So voltage divided by the total resistance. That gives us our current. So we have 1.2 amps running through the whole circuit. So that's our I value, and now we just need to multiply that by our voltage value, which is 12, and then we can get our 14.4 answer. So that's where that one comes from. I will be honest, it's been a while since I've done electronics. The first time I did this one, I also messed it up. So that's reassuring, isn't it? But yes, so that's the correct answer there, is 14.4 watts. Lovely. All right, on to our next one. I think this might be, yeah, so this one is the last mathsy one, I think. Look at that, Maria's on a streak. I believe Phil probably is as well, but look at that. Fantastic. A bit more movement. Kate's back on the leaderboard. Fantastic. All right, here we are. Yep, so here's our last one. I believe this one is very similar. So this is actually a bit different, isn't it? Yes, so in this case you have 12 volts here. Your second resistor is 15 ohms. The total resistance of this whole circuit is 150. And then you need to find what the voltage across just R2 is. So to get that, you need the current through R2. And once you have the current through R2, you can work out the voltage, because you know the resistance of R2. But first, to work out that total current, you need this total resistance value. So this one's a bit tricky. And I've realized there may not have been enough time for it. That's all right, we'll work it through afterwards. Hey, look at that. So we got a couple of answers there at the very last minute. And it was a bit quick, I assume, for everyone else, which is entirely reasonable. So the correct answer is, as the people who put it in suggested, 1.2 volts. Now, the reason for that is, I can show this here, and then we can work through it together. As I pointed out, and I apologize for explaining it probably a bit too slowly when I was explaining it verbally. That might have been distracting. But this total voltage here is 12 volts. So there's 12 volts running through this whole thing. The total resistance is 150 ohms. So you can assume that R1 plus R2 is 150, because that's the total resistance. And then it's just asking what the voltage across R2 in particular is. So if we want to know the voltage across R2, we can look at a relation that relates voltage to resistance, and that is Ohm's law. So here we see, okay, here's the voltage. This is what we would like to know. And then we can see here is the resistance, which is 15 ohms, because we've been given that. R2 is 15 ohms. And we don't know the current. However, if we could find out the current, then we could get to our correct answer that we want, which is our voltage answer. So in doing that, well, first let's do that. Let's find our current, right? So our current, we just used Ohm's law again, except now we're using this total voltage of 12 volts. So we take our 12 volts divided by the total resistance. So total voltage by total resistance. Our total resistance was 150. So our current would be 0.08 amps. Now, what we want to do is find the voltage in this particular resistor. Because current doesn't disappear anywhere in this loop, so the current here is the same as the current here is the same as here, same here, same here, same here, all the way around the loop, because it's just a single loop. So in this case, then, what we know is that the current through R2 is 0.08, because that's the current in the whole loop. So we take our current in that resistor, multiplied by that resistance, which is 15 ohms, and we get out of it 1.2, and that is our voltage value. So that's how we get our 1.2 volts. I realize that one's a bit squirrely, so I'll ask in a poll, does that make more sense? And I reckon most of you probably could have figured that out. It was just kind of very quick, for which I apologize. Okay, cool. So it looks like that makes sense to people who answered there. Wonderful, excellent, cool. So I'm glad I could hopefully clear that up. Yes, so 1.2 is the correct answer there. This last one, relatively easy compared to the rest. It's no longer a mathsy one, so get out your speed. Last question, it's a true or false. Leaderboard holding steady. Look at that. We're pulling ahead a bit more. All right, true or false? if the supply voltage is 12 volts, is the voltage across R1 and R2 also 12 volts? And here's the circuit. Hey, look at that. Yes, you're all correct. It's true because these are in parallel, so the voltage across these two components will always be the same because they're in parallel. If they were in series, it'd be different, but these are parallel, so yes, it is true. Excellently done, everyone. So let's take a look at our results. Dun 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 dun. In third place, we have Ange. Look at that. Very well done. 5 out of 6. 6 out of 6 with Phil. And same with Maria. Very impressive. Our ultimate winner of the day. Very fast. All correct. Look at that. Absolutely wonderful. And we have our runners up here as well. Absolutely fantastically done, everyone. Hopefully that was a little bit of semi-competitive fun and helped clear up some of these equations for people. With all that out of the way, do people have any lingering confusions that I can help clear up about any of this? Any questions, or are people feeling pretty alright about it? The Kahoot theme song is also very catchy. That's going to be in my head for the rest of the day now. There's an orchestral version of it. They're also on Spotify. More you know. Alright. Stellar. Okay. I will assume no questions. If there are, of course, just let me know later. And we'll power onwards here. So, Kahoot quiz. Well done. We've done that. Now, we can get into some other things that are good to know. These are called Kirchhoff's laws. Sorry. Tried breathing my own spit there. That didn't work very well. But Kirchhoff's laws are two laws that let you find lots of unknowns in different circuits. So you might be given a circuit, and you know the resistances of things, and you know the voltage of something, but you want to find the current in some particular area. But maybe the circuit's a bit more advanced than these single loop ones that we've been looking at so far. So this helps us work that out. So there are two laws, first of which is the current law, and this says that all the sums of all currents at a node is equal to 0. And a node is just a place where wires branch or where wires come together. And it makes a decent amount of sense to say this node were a hallway or something, or a corridor. And you had people coming into the corridor, then the same number of people coming into a corridor in a certain amount of time, provided the corridor isn't like filling up, if there's a constant amount of people there. So the amount of people going left and going right is the same number of people that are coming down the road in the first place. Because the people coming here aren't going backwards or anything, they're just coming in and then they're picking a path to go. But in this case, I1 plus I2 is equal to I3. So the current in is equal to both of the currents out. And this just shows that it doesn't actually matter which direction you put these arrows. So here it looks like everything is going out, which wouldn't make sense. You can't have people just constantly leaving a corridor in all directions, unless you have some way to spring people out of thin air. But that's not a problem because currents can be negative. So we see here that the signs are different between these two, and that's because here, I5, for example, could be a negative current. So if it's a negative current pointing this way, that means it's a positive current pointing the other way, which means you still have things flowing into this node and things leaving it here. So these arrows that you put on are not terribly important which direction you put them. Just make a guess when you're doing a circuit, and if you get a negative number, then you'll just know that it's the opposite of whatever you guessed in terms of the direction of the current. So there it is expressed in the fancy mathematical form, just saying all the currents at this node equal to 0. Very similar looking law, but with voltage. All the voltages in a loop are equal to 0. And that kind of makes sense because you have to get back to 0 somehow. So if here you have 6 volts and you go through a couple things, by the time you get at the other side, you have to be back at 0 volts. Otherwise you'll have 6 on both sides, and then this difference won't actually be anything. So in this case, you can see that there's 6 volts going forward, and resistors always work against the current, so they have a negative voltage in this case. So you're subtracting 2 here, and you're subtracting 4 there. And that's how you get back to your 0, because 6 minus 2 minus 4 is equal to 0. And that's around a loop. Excellent. To apply that, we have an example problem. So the question here is, what are the currents? And you can see there are a couple of strange things going on. So not only is this a slightly more complex circuit than we've looked at so far, but there's this second power supply here. And that's the real bit that throws a wrench in things for us. So how we solve this will probably be mostly mathematical. So I think for this, what I'll do is get pretty creative. And we're going to try and turn my webcam into something that looks down at a piece of paper. And then we'll go through it together is the idea. So I may... By the way, I'm not entirely sure how it works on your end. Can you see my face just as big as you normally would be able to if I weren't presenting? Or should I stop presenting temporarily so that you can see whatever's on the webcam? Just let me know in the chat which of those I should do. In the meantime, I'll be assembling my exciting camera rig. Okay, we can pin you and see you full screen despite the presentation. Fantastic. Can everyone figure out how to pin me, like Kate has done? Also, get ready for some exciting webcam acrobatics. Hi, I'm upside down now. Put that. This bizarre system I got figured out here involves hanging things off of books. It's a bit bizarre, but might work all right. So, cool. Can you see, not that I have a notebook to put there, can you see this notebook that is there? Can you see when I write things on it? Wonderful, fantastic. And it's the right way up, right? It's not upside down. Only the top of the notebook. So only this bit. You can't see back here, or vice versa. Can you see this bit? Distant bit. I wish I could see my own. I can only see where your pin is. Got it. Okay, cool. So I will move this then this way. Can you see more of the notebook now? Excellent. So you can see down here, you can see the whole thing. Stellar. I wish I could see my own camera. Okay, almost the whole thing. That's good. If I go off, yell at me, I guess. Well, yeah, sure, feel like it. Go ahead and yell at me if you want. All right, so I'll start by solving this problem by drawing out the circuit itself. So actually, it occurs to me that we've not, strictly speaking, looked at a bunch of these like circuit diagrams before, so I'll explain what things are as we go along. So on the left side, we have the lines, as you might expect, are wires. So those are just wires connecting things. The plates thing here, where you have a tiny plate and then a big plate, those are batteries or some sort of power source. So in this case, it's a 3-volt one on this side. The big plate is the positive end, and the tiny plate is the small one. Sometimes people will go ahead and be kind to you and label, like with a little plus, which side is positive. Other times they'll just leave you with that. But if they do leave you with that, remember, tiny one negative, and the big one's the positive one. Then we'll go ahead, we'll draw down here. Then we have in the middle. Now I'm going to draw this resistor in the middle a bit differently, because I think that's how they do it in the UK. What they have here on the screen, this example problem, is a squiggle, like that kind of thing. That is how the US, the USA, United States, writes resistors in their schematics. But technically, because that's a bit ambiguous, there's another schematic diagram that we'll look at later. There's an appendix to this PowerPoint slide. Because that can be confused for a resistor, the international standard is now to write resistors as rectangles. So a resistor would look like that, and then you could go out the other side, connect it up here. So this resistor is 75 ohms. So doop, doop, doop. Wonderful. And then over here you have our second one. This one's got a resistor here, and it also has a power source, or a battery kind of thing. And that goes that way. And I do apologize in advance for my horrendous drawing. There's a reason I ended up in engineering and science and not in art. All right. Excellent. Wonderful. So I think that's the example problem written down. So now our goal is to find these different currents. So we have one current that comes out of, that's going along this loop line here. So we'll call that one I1. So that's our first current, and that one is this way. So that's the first current, and that's a bit nicer labeled on the example problem itself. Down the middle, of course, you have I2, and that's going down just this middle resistor. And then around this outside one, we have a current going this way around the loop. That is I3. And that's going around and through here and back out there. And again, these arrows, the directions you point them, entirely arbitrary. It works out either way. So what we'll do first is apply Kirchhoff's voltage laws and walk around these loops. So we can label the loops. This one is loop 1, and then this one over here would be loop 2. Again, those are just arbitrarily numbered, but this loop here is just, well, it's the literal definition of a loop, I suppose. It's just any circuit like this that can be closed. So that would be one loop, and then this one here is the second loop. So what we can do is walk around, and then we'll add up the voltages as we go along. So first thing, we'll start down here, and we'll walk up this line. We run into a battery here, and we're going from negative to positive, so we'll have it put in a positive number. So we'll write for loop 1, we'll start with positive 3 volts. So there's our 3. And these will all be in volts, so I'll leave off the V. So we have our positive 3 volts. We walk along up on the top, nothing there. Then we walk down here, and then we encounter a resistor. Now, because this resistor is going against, or we're walking with the flow of current, the voltage value it gives is going to be negative. So it's going to be minus, and then what's the voltage on a resistor? Well, we know that from Ohm's law, which I'll rewrite here. Hopefully that can be seen. So it's just voltage is equal to the current times the resistance. So in this case, we just do exactly that. I'll switch the order of them and I'll write in the 75. So we have 75 ohms, which is the resistance, multiplied by I2. And we don't know what I2 is just yet, so we're going to leave that as a variable, I2. And then we continue going around the loop, and then we're back to the same starting point. So there's nothing there. So we know that that is all equal to 0 from Kirchhoff's voltage law, because Kirchhoff's voltage law, remember, says around any closed loop in a circuit, the sum of all the voltages is 0. So here we have a positive 3, which means over here you must have a negative 3 somehow. And that negative 3 comes from this equation here. So now what we can do, actually, since this is a loop that only has one variable, we can go ahead and solve that equation. And we can just do that by rearranging. So let's add 75i to both sides, and I'll flip the sides. So we have 75i 2 on that side is equal to 3, which of course just goes into, once you isolate I2, I2, and then 3 over 75. So that is actually one of our answers already. So that's the current running down this middle branch here. So if that's all we needed, then we could use this current value here and get some answers. And I'll even do that on a calculator. I believe it's, well, I'm not going to guess what that number is. I saw it earlier today. So I'll just do 3 divided by 75 and get back 1/25. Thank you, Casio. 0.04 amps. Wonderful. And remember, these are amps because we're using standard units everywhere, voltage and ohms. So that's our amperage value for I2. Then from there, we can walk around the second loop. Let's go ahead and do that. So we'll start up here at the top, and we'll walk around this way, just semi-arbitrarily. So L2. First thing we do is we walk into a battery, but this time we're walking into it the opposite way. So instead of going from negative to positive like we did before, we're going from positive, which is this big plate, to the negative one. And what we want to do there is make it a negative value. So instead of being positive 12 volts, it's actually minus 12 volts. So that's what we have when we're coming into this top bit here. Then you encounter a resistor. This is, again, we're following the current, so this is going to be a negative voltage from the resistor as well. So that is going to be similar to what we saw before, except now it's a different current. It's I3 and a different resistance, 125. So it's going to be minus 125, 125 I3, which we have there. Then we keep going around the loop. Then we encounter this here. Now this is curious. We're encountering a resistor from the opposite direction. So this current arrow is pointing down, but now we're going against the current instead of with it. So because we're going against the current, we need to flip the sign. So normally resistors are negative, but now we flip it to be positive. And then it's the same as we saw a second ago, which is 75 I2. Now, this I2 value, we actually have a concrete value for, remember, now, which is convenient, which is also, very curiously, over 75. Well, perhaps not curiously, but very conveniently. So what we can do is just plug in that value directly. So 75 times 3/75 is just 3. So if I go ahead and do this, you end up with a plus 3. And then you have the same mess over on this side. Then you can combine the negative 12 and the 3. And remember, of course, sorry, this is all equal to 0. So that's our basis for modifications here, or manipulations. And we want to isolate I3. So first we will move this 3 over to the other side of the equal sign and do the same with this 12. So we'll subtract 3 and then add 12 on one side of the equal sign. And then on the other side of the equal sign, we have our 125, I3 still. We'll stick those together and we get 9 when we stick those together. And then we'll just divide 9 by negative 125. And we'll get I3. There. And that works out to be, we'll find that, 9 divided by negative 125 is going to give us, thank you, very helpful, Cassio, a negative current, so negative 0.072. Now, this negative number is a bit strange. That's, negative current is a weird thing. So what does this negative current tell us about the real state of this circuit versus our diagram here? Does anyone want to give that a guess? What does this negative current mean functionally if this I3 is negative? Any ideas? Anti-clockwise flow. Yes, excellent. So yes. So in this case, what I'm doing with this current arrow is showing that the current is traveling clockwise, which is this way. But since this number is negative, that means that my guess was incorrect. So the guess, or the current, is actually flowing up this direction. So the current is going this way through the circuit. So that's what the negative number means. Fantastic. Then if we want to find I1, we could faff around with these maybe some more, but a much easier way to do that, now that we have I2 and I3, which are here and here, is we can just use the current law. So let's take a look at a node. Here's a node, and the things coming into that must be equal to the things going out of that. So coming into it, we have I1. So I1 equals, and then going out of it, we have I2 and I3. So I2 and I3. And then that's a very, very, very simple calculation from there. Just taking our two numbers, adding them together to get our final current of, so let's see, we had 0.04 plus, which is actually minus because it's a negative number, 0.072. And we end up getting 0.032. So the second negative number here for our I1 means that even this arrow is wrong. So this voltage supply must be being overpowered by this much larger one. So in fact here, the current is also going down and anti-clockwise. So that is a worked example of how you can apply these rules. And that's applying a whole bunch of our rules, actually. How are people feeling about that? Because if you've not seen that before, sometimes that's a bit difficult to grasp. Or perhaps a bit disorienting at least. I'll quickly move this to type on my keyboard and write a poll, and then we'll see how people are doing. Poll, how, all right, I'll put this back so we can see it. Hopefully that's in about the right place. And if there are any questions, do feel free to ask. I am happy to re-explain any bits that might have been missed there. No worries at all. Wonderful. Okay, so people seem to be doing overall all right. Is there a holdout on being all right, or is there just someone who hasn't gotten around to the poll yet? I'll give it another second in case anyone has questions that come up. Okay, wonderful. We're back up to our 6. Stellar. Okay. Lovely. In that case then, I'll head forwards past that. I might, let's check what's my next slide. Yes, okay, so my next, I no longer need my wacky setup here, so I'm gonna flip my webcam back over. Whoop. And hopefully maybe we can see me again, or at least my shirt. Probably a gross, unshaven mustache. I'm sorry. Work demands scraggly facial hair. Alright. Wonderful. Cool. Maybe I can be seen by that webcam. We'll find out. It's not too terribly important at this point. It's just the screen share. Okay, excellent. So, oh, hey, we've moved all the way to the challenge exercise, so I'll leave that for later. So our next thing to do, and this is probably how we'll wrap up, we'll do one of these, I think, as an example, probably. And then I'll leave the rest as an exercise for you lot to create. Out of all of these circuits, which one of these would you like to have me create for you now in Tinkercad? And we'll go through it together. Because the rest of the other two schematics that we don't create together, and we're going to put these on a breadboard. So we're translating schematics to breadboard. Which one of these would you like me to go over? 1, 2, 3, or left, middle, right. And we'll go through one of those now, and then the rest I'll leave as an exercise for kind of building and playing with. Or actually, middle? Hey, fantastic. I'm glad you chose the middle, because I was just about to make the executive decision to choose the middle, because we've just done the calculations for it, so theoretically, we should be able to measure the numbers that we just calculated. So I think that's a good idea, Philip. First to it, you win in the world of democracy. All right. So I agree, let's build that circuit. That's gonna be exciting. That's all right, we'll split it part and part. So up on Tinkercad, and we'll zoom out. That's not gonna work at all. That's all right, we'll improvise. More windows, more windows. And stellar, and circuit, and we'll wipe it all. Is that allowed? Oh, do I have to select everything? Is that even possible? Right. We will create a new one. Unfortunately, I'm not an expert with it yet. I'm loving all the names, though. Okay. Amazing Crunk. I agree. Whatever that means. All right. We'll start with a breadboard. And I'll go ahead and zoom that in a little bit. And we'll push this way so we can have a bit more breadboard, a bit less schematic. Oops. All right, so here's where we're starting. First place to start is with a voltage supply. Now, we have at our disposal a 3-volt battery. I'm wondering if there's actually a general voltage supply. So if I search voltage supply, they've got particular batteries, they've got other components, they've got a power supply. Sure, let's play with a power supply. Now let's put it together with batteries, why not? So, in the real world, you'll probably encounter a similar issue. If you want, say, a 12-volt power supply, you'll need to get something specifically made for 12 volts, or combine in series batteries. So that's what we'll do here, I think. So we'll take our 3-volt one. That one's easy enough. We have a 3-volt thing in our loop, so we'll just use that directly. So we'll put our 3-volt battery there. And I'll connect it up, say, here and here. Or I'll do it out there. It's a bit nicer looking, isn't it? Oh, no. Tragic. There we are. Wonderful. Okay, so there's our left side of the schematic. We have our voltage source here, positive voltage up, 3 volts over. Now we want a resistor that'll go between things. So we can actually put our resistor like that, I believe. Now, this, it's important to note, this middle line of a breadboard denotes 2 separate halves. So this row 20 here is not connected to this row 20. And you can see with the highlights, those are separate. So this middle bit is a big break. And that allows you to put some particular components on. So this, it's not connected to itself. Instead, this top end is connected to the 3 volts like we see here. Then it's the resistor in the middle. And then this line on the bottom. Now what we can do is, of course, change the resistance of that. We want 75 ohms. Let's go to ohms, and go to 75. Go ahead and put that in. Wonderful, 75 ohm resistor there now. So that part's done. Now we just need to look at the other half of this circuit. We'll start with the resistor because that's the easier bit. So we'll go over, let's say, here, arbitrarily. In the real world, you might want to make these things smaller so you have more room in your breadboard. Just depends on how much you're putting on there. Then here, we'll put on a resistor that connects to that and to something else. And this value is 125 ohms. So 125 ohms. Wonderful. Now we get to the tricky bit, which is our power supply. Because we don't have directly a 12 volt one available. We have a 9 volt battery and we have 3 volt coin cell though. And those together add to 12. So something I haven't shown you explicitly, but that is implied, I guess, by all of Kirchhoff's voltage laws, is that voltages add in series. So if I take a 3 volt battery and a 9 volt battery, and I connect, oh my, did not mean to connect them to that. So if I go, I'll probably have to zoom out a little bit here. Oh no, there we are, that's fine. Okay. Sorry, I'm like a grandma moving around this. Okay, so there we are, wonderful. What you can do in these batteries is connect them in series. So one after another. So if you imagine the power coming out of the positive end here, which is how you traditionally view current flowing, is coming out of the positive end of a battery. It'll go out of the positive end. We want to put it into the negative end, so it gets reboosted by this battery and comes out of this positive end again. And what that does is it adds this 3 volts to this 9 volts. So I'll show that to you now. I'll flip this around just for the sake of simplicity. So I'll flip that around, draw a wire connecting the positive to the negative, and then we'll use a multimeter to measure our voltage. So voltage, there's one voltage, and here's the other voltage. And you can see combined, those are going to be 12, or negative 12 because I've connected the multimeter backwards. See, I've connected the red to the black, but that's fine. So together, those will give us 12. We do want to be sure that our direction is correct, though, in our actual circuit. So I will need to flip both of those around. But for now, we can stop our simulation. We can chop that away. Come over here. I'll just do this and spin it around. And I'll spin this one around just for the sake of it. There we are. It's really not helped a whole bunch, but that's fine. Cool. So the idea is that we have coming out of this. Yeah, it's very ugly, isn't it? That's fine. The positive end of our combined battery, which is now these two things together, up here, is supposed to be on the top part of the circuit. So that should actually be connecting over to this line eventually. So I'll just draw a line over here that connects those two rows. Although actually, so that would be incorrect because that would be putting these things in parallel. So I'll put it here. So this is drawing this top stretch of wire here. Now we need to put in the battery. So we first put in the positive end, which is this end here. So positive end gets connected to that. And then it's the negative end of the battery that gets connected to the resistor at that line. So positive end up here, then the negative end is connected to the resistor, and you can see the black connected to the resistor. I will admit, this is like the ugliest tangle of wires I've ever seen. There we are. In the real world, obviously, how it looks doesn't matter a whole bunch. However, if your circuits end up really, really messy, it can sometimes be hard to see what's connected to what. So I do implore you to, in the real world, make clean circuits, but you don't have to. And that's no worries, heading off really totally fine. Happy to help. Yes, we'll be wrapping up here as well. I'm just going to measure the voltage on these things to double check our calculations, and then I think that'll be all for today, unless anyone has any questions. So, real quickly, we'll do that. So let's do, say, well, actually we want to measure current, don't we? Because current is what we calculated. So, or actually, we could calculate a voltage as well, because voltage is a bit easier to measure. So, before, down this middle bit, we calculated I2 to be, and this is me checking my notes because I've entirely forgotten, I2 is 0.04 amps. So 0.04 amps is what I2 is. We also have a resistance. With a voltage and a resistance combined, we can get... Oh, I've closed it. My calculator. So with a voltage and resistance combined, you can get a... Or sorry, I misspoke there. With a current and resistance combined, you can get a voltage. That's what Ohm's law says, because V equals IR. So if we multiply our 0.04, which is our current, by our 75 ohms, then we should get a voltage across that of 3 volts, which actually is exactly what we wanted it to be, because remember, this loop has to have 0 volts in total. So this is the plus 3 there, and then it's minus 3 here, and then you're back to 0. So let's check and make sure that this middle resistor here has, in fact, 3 volts running across it. So we'll just take our multimeter out to prove to ourselves. So multimeter there, and we'll connect the negative end to the, let's see, so the voltage goes from high to low. I'm not sure about the polarity here, but that's all right. Plus minus usually doesn't matter here. So there it is in parallel, essentially, with that resistor. And now we can go ahead and run the simulation. And we get out of it, something slightly larger. So we have 3.21, which is a bit curious. So that could just be a strange effect of the way we've done our calculations, or it could be me typoing something somewhere. But I think in this case that might just be the batteries perhaps having their own resistances in, because I assume these might be actually some quite large currents running through here. Okay, but that is somewhat in the ballpark, at least, of what we're expecting. We can try and measure a current, I suppose, as well. So to do that, we would need to... so we need to put it in series for current measurements. So for current, we can move this over one here. This can still be connected up to that, but now you see it's not connected to either of these things, but in between those, so in series, we'll put the multimeter. So we'll have that, and that connects to that. So now the electricity goes down, or the current comes down here, into the resistor on that end, then it has to go through the multimeter first, then it comes back here, and then it can go back into the circuit. So in this case, we'll change this to be up at amperage, and then start the simulation, and we can see that number there, which is that around what we expected? Yes, actually, so that's not too bad. So because remember our 0.04 is in amps, so to get to milliamps, we multiply by 1,000. And of course, our number we get to there is 40. So there's our 40 milliamps, and you can see that's slightly different, probably because this is simulating some real-world imperfections. But you see that's very much what we were going for. Cool. So that's how you would build that on an actual breadboard. You could probably do this much cleaner than I did here, but the important part is just that the functionality is the same. I think that is basically all we've got to go over today. I will pose to you a nice, fun challenge exercise here, and I'll put the answers for this up on the website of resources when I put that up later today, with the recording as well. But this is just a more challenging exercise. You want to find what this value of V3 is, so this isn't actually connected here. Those are just open ends of a wire, and just find out what's the difference between those two in voltage. And then also, what is this current here? And, interestingly, working the other way, what voltage do you need to make this current 0? So that's your little challenge exercise. I've got answers to that I'll put up. That's just using Kirchhoff stuff. But that is that. Lovely. Aside from that, here's some symbols that you might find in circuits. Don't bother memorizing them, but sometimes they're helpful to see. So there's our resistor, which is our square thing. There's a, so batteries are technically multiple different cells, but you can sometimes just show single cell ones. So there's a battery or a cell. Obviously, wires are just these connecting lines here, and I don't think we've actually played with too many of these other things. But there's an inductor. That's what resistors can look similar to if you're looking at the US drawing of things. And LEDs, they look like this. So this A here is the anode. So you can think of this big triangle as being an A if you extended these legs. So that's the anode. That's where the electricity comes in. So that's the positive end. That's the bit that shows it light emitting, or those little arrows going off. Those are little light rays. and that's the negative side of things, the giant minus sign. So power goes through it that way, and then it lights up. Lovely. And there are other ones you might come across at some point, but you don't need to have them memorized particularly. Just know that there is a standard kind of language. If you see something bizarre, you can look up something like this and see, well, that's just a switch or a variable resistor or whatever. Wonderful. Cool. So I think I'll wrap it up there. We're just definitely at our time. Does anyone have any questions I can answer about anything at all? And I'll also do a little bit of an exit poll here. And these slides will be up on the website, and I'll put those up on, I'll link the website again once those are up on the Discord so that you can see this challenge exercise and you can let me know how it goes in the end. Wonderful. Cool. Does anyone have any questions or anything I can help with? Next week we'll have Arduino. So we're going to take all these circuit things. So far we've just been doing like kind of the gross slog work mathsy stuff. But next week we'll actually get to build some cool things and control them with some programming. So we're going to learn to program in a slightly different language from Python, which is how you program Arduinos. And those microcontrollers, which is what an Arduino is, they let us automatically change things with circuits like this. So we could build all sorts of things. We could build like a traffic light that changes between a red, yellow, and green LED, or all sorts of different things like that. But yeah, so that's next couple of weeks will be Arduino stuff. After that, it's 3D design. But cool. I'll just leave it for questions, and if there are no questions, then I hope you all have a lovely day, and I look forward to hopefully seeing some of you next week again. Well, seeing everyone virtually, I suppose. Maybe someday I'll get to meet you. Hopefully so. Cool. Any other questions? Cool. And remember, if you're doing the challenge problem and you hit any walls, because this is not necessarily the easiest circuit in the world, it's a bit tricky with just the Kirchhoff rules to solve, but you can. It's just tricky algebra is all. Or not necessarily tricky as much as it is just long. But if you run into any walls, feel free to just post on the Bootcamp channel that you've had some issues, and I'll help you out. But yeah, cool. That is that. I guess technically, if you can solve this, then you're you qualified up to part of the first semester of EEE 123 at University of Sheffield. But yeah, take care, Philip. See you. All right, I will leave things there. But yes, it was lovely seeing you all, and thanks for coming along. See you. Wunderbar.